A very good morning, one and all. I welcome you for session number 22. LCR series resonance circuit. Let's recap what we studied in the last class. You have seen in an LCR series circuit, the vector impedance is the sum of R, L, and C. The current is given by I is equal to I naught e power j omega t minus theta, where I naught is given by I naught is equal to epsilon naught divided by square root r square plus omega L minus 1 over omega c whole square. This particular term is called as impedance, and depending upon the value of omega L and omega C, we are seeing the phase differences between voltage and current. The phase difference is given by theta is equal to tan inverse of omega L minus 1 over omega C divided by R. In the case 3, we have learned when omega L is equal to 1 over omega C. Substituting the value in this particular expression, we will get Z is equal to R. Then it acts as in a pure resistance circuit. Then the phase difference between current and voltage is given by theta is equal to 0. Then that is called as series resonant circuit. The main objective of this session is to understand LCR series circuit, bandwidth, quality factor, and the properties of series resonant circuit. By the end of this session, you will learn what is LCR series resonance circuit and the properties of series resonance. LCR series resonance circuit. We know that Z is equal to square root R square plus omega L minus 1 over omega C whole square. For omega L is equal to 1 over omega C, Z is equal to R. Then the current is maximum, which is given by I max is equal to epsilon over R, and the circuit is said to be an LCR series resonant circuit. A circuit in which inductance, capacitance, and resistance are connected in series, and the circuit admits maximum current corresponding to a given frequency of an AC is called series resonance circuit. For that particular value, which is for that particular omega, which is represented as omega R, then the condition for series resonance is omega L is equal to 1 over omega RC, and multiplying omega R, and then omega R becomes 1 over root LC, and the frequency is given by nu R is equal to 1 over 2 pi square root of LC. This particular frequency is called as resonance frequency. The frequency at which the current becomes maximum is called as series resonance frequency. And if you plot a graph between the current and the frequency, is known as resonance curve. Look at this picture. Along the x-axis we have frequency, and along the y-axis we have current. For a particular frequency Fr, which is a resonant frequency, the current is maximum. However, if you apply the frequency less than the resonance frequency, then the current is given by I is equal to V over ZC. It acts as capacitive circuit. For a frequency greater than this resonant frequency, it acts as an inductive circuit. And the shape of this curve is like a bell shape. Likewise, if you plot a graph of frequency versus or impedance, we have seen as the resistance increases, so as the frequency increases, the impedance starts decreasing, reaches to a minimum and starts increasing. For a frequency less than the resonating frequency, it acts as a capacitive circuit. If the frequency is greater than the resonant circuit, it acts as an inductive circuit. Now we have seen how the frequency affects the current as well as the impedance. So we learned about XL and XC. Now we learn about how the resistance affects the current. For a frequency of larger frequency, the curve is a shape which is broader. If the resistance is decreased, then the bandwidth starts decreases. For a resistance which is very small, the bandwidth becomes very small and the shape of the sharpness of the curve increases with the decrease in the resistance. And next we'll learn about bandwidth of a circuit. So at resonant frequency, the current is maximum, which is I max. So divide over root 2, you have 0.707 I max. If you plot a line, it curves at two particular points, 1 and 2. And this point let me represent as F1 and this as F2. The differences between these two frequencies greater than resonant frequency and less than the resonating frequency. The difference between these two frequencies is what we call it as bandwidth. For a fixed value of L and C, from figure it is observed that maximum value of the peak current is inversely proportional to R. For lower values, I is large and vice versa. A series resonance circuit admits maximum peak through its at resonant and it is called as acceptor circuit. Due to fact it accepts only at this particulars and rejects the other one. The sharpness of the resonating curve we are seeing as the resistance changes. Q factor or sharpness of resonance is defined as the ratio of voltage across LRC to the applied voltage, which is voltage across R. It is given as 1 over R square root of L over C and it has no dimension. The quality factor may be Q factor. Q factor is taken as voltage multiplication factor in case of series resonance circuit. We have seen quality factor is directly proportional to the sharpness. The quality factor, the Q factor, decreases with resistance. The bandwidth, the difference between the two frequency is upper frequency and lower frequency is called as bandwidth. The relationship between bandwidth and Q factor is given as Q is equal to omega r divided by 2 delta omega. The ratio of omega r to the 2 delta omega is the measure of sharpness of the resistance. Note that the higher value of Q, narrower and sharper is the resonance. The properties of series resonance circuit we have seen. The resonant frequency in case of series circuit is nu r is equal to 1 over 2 pi square root of LC. At resonance, the power factor is 1 because Z is equal to R. The phase difference is 0. At resonance, the impedance of the circuit is minimum while the admittance is maximum. Series circuit admits maximum current at resonant frequencies. Series circuit is called acceptor circuit because it accepts at a particular frequency and rejects others. At resonance, the circuit exhibits voltage magnification to the quality factor. So in this session, we learned the condition for a series circuit to be at resonance is omega L is equal to 1 or omega C, whose resonating frequency is given as mu r is equal to 1 over 2 pi square root of LC, and it is called as acceptor circuit. The quality factor, a Q factor, is given as omega r divided by 2 delta omega is equal to omega r L or R, and the bandwidth, which is the difference between the upper and lower frequency.